I've hired a lot of really great ICME students. In fact, the way I met Karen is through an ICME student. He was doing really well in my group. It was a small group then. And I asked him, where can I find more of you? And he said, I think my classmates were all similar to me. So he said, okay, I'll introduce you to Margot. And at that point, Karen had just taken on, I think, the partnerships for ICME. And that's how I met Karen. So today, I actually was going to take you through building an AI product, not just designing it, but executing it. And it's fairly simple. I mean, so you should be able to easily follow along, and I really welcome questions along the way. But the idea is people who have not worked in the industry often think that they have one of two thought processes. One is there's not really much AI going on in production teams. And even if they're doing anything, it's like black box AI, like they just use open shelf tools and build something. And that's not the case, especially in really large companies, as well as in the online advertising space, which has always been at the forefront of AI. And the other piece is, there's not much R&D going on in these products. And in fact, a lot of the R&D actually happens in these products because they are actually user facing and advertiser facing. And when you want to run experiments, that's the population that you want to run the experiments on. So a lot of the work that we do, in fact, is very heavily R&D focused, and we work with MSR, Microsoft Research, in all locations in Asia, India, and in Bellevue and Boston. So I just wanted to give you a sense of the fact that, the stuff you're learning right now in your classroom, you will be applying it when you join one of these AI products. And so that's where I wanted to get started with. So what's the goal? Let me see if I'm able to, there you go. What's the goal for today? So we are going to design the objectives and metrics of an AI-driven product from scratch. Given these objectives and metrics, then we are going to actually engineer that solution and then talk through what are some of the data and modeling challenges that you have when you're engineering the solution. And say now you have constructed the product solution, it's out in the market and users are using it. Now, how do you maintain this product at steady state? So deploying the first AI model is just the beginning of your challenge. You've got to maintain it and you've got to iterate on it and you've got to update it as users interact with your product, as you add new features to your product. So we'll discuss all three of them. And obviously I'm like a 1,000-foot level for each of these. So feel free to ask more detailed questions, or if there's a lot of interest, I can take one specific thing and maybe deep dive in the next semester of this CME500. Okay, so we'll start with designing an AI product, and I picked advertising because I've designed an advertising product. But we could, you could take your favorite app that your startup mind is already thinking about, and you could go through the same process for your app. So let's look at who's going to work with this app. So I'm talking about an advertising product. So the participants in my ecosystem are advertisers. The advertisers are going to come use my product. And what do they care about? They're going to put marketing dollars into my product and ask me for either clicks, conversions. I call them purchases here, but really, users coming and doing something valuable on their site. Brand awareness, they just want their brand to be well known. They want some return on spend. So it's not just that they want the maximum number of conversions. They may want those conversions at some margin. So that's what return on spend typically means. So they may have a bunch of different goals. Obviously, I've built this app, so the users are going to come and interact with this app, and those users want relevant results. They want good product pages. If I can provide coupons or savings and I can make the purchase more economical, the users would really enjoy that. So those are the users who come to the app. And then I'm the app, I run the app. So say, the app is a search engine. In most of the examples I'll use a search engine, but it could be a gaming app, it could be a social app. In any case, the app is typically referred to as the publisher. You're sitting in the middle, you're connecting the users up with the advertisers. And what do you want? You want really users to engage with your product, your user growth to be consistently growing, and you want to make revenue. You want to really make long-term revenue from some source, from subscription or from advertising. We're going to use advertising here. So what's the blue sky objective for you as the app creator? You want to maximize long-term revenue. And so let's break down revenue into its functional elements. So revenue is a function of the number of users who come to your app. Each of these users engage with your app. If it's a search engine, they issue queries. So there's queries per user. For each of these queries, you may show or choose not to show, but you may choose to show some ads. Now, if the user clicks on this ad, then the advertiser pays you some cost. So that's a cost per click. So if you break this equation down, you will quickly notice that three of the components, the users, queries per user, and clicks per ad, are a function of the user and the system. So as the number of users grow, the more they engage with your app, you should be seeing your revenue rate, going up. So it's a function of the user. Obviously, it's a function of the system because you need to show ads, relevant ads to these users, so that they click on it. And then obviously you need advertisers in your ecosystem so that the ads per query, the density of the choices you can show to the user, as well as the cost that the advertiser is willing to pay, that's a function of the advertiser in the system. Now it's a function of the advertiser and the system because the system will typically run some kind of a ranking and pricing mechanism. That's the auction, the ad auction that runs. So that's where the system comes into play. So let's take that as this is what we're trying to do, long-term revenue, and then let's come up with a formulation. Okay, so we need to come up with, okay, how am I going to do this long-term revenue? So we'll make two assumptions. What the first assumption we'll make is that if the user is happy with your app, satisfied with your app, they will engage more with your product. So what we'll do is we'll take long-term user engagement. Obviously, if you can build a model for long-term user engagement, that's better. But let's take short-term user satisfaction as a proxy for long-term user engagement. And this means that you need to come up with these satisfaction metrics. So we will design the metrics just in a bit. The second thing is, for most apps, the daily, weekly, monthly user growth, it's the DAU and MAU are key watch metrics. So even as you're making money to sustain your business, you really do want to see your user growth. So you need to pick those metrics that really match that user growth. That's your long-term user growth. The second assumption we'll make is similarly on the advertiser side, that if the advertiser sees the right ROI, they get the right conversions, clicks, brand awareness, whatever their goals are, they will increase spend in your ecosystem. And so again, you're going to use short-term advertiser satisfaction as a proxy for your long-term advertiser spend. And advertisers are typically watching for ROI, but quite frequently, they are also watching for traffic growth. So these are correlated metrics. So if your users are growing, typically advertisers are more inclined to come to your platform because they see a growing product and they want to be part of that growing product. So you have now your short-term user metrics that you're going to derive, short-term advertiser metrics that you're going to come up with, and then you want to maximize all these three metrics. You want to maximize your revenue, your user satisfaction, and your advertiser satisfaction. And they're frequently formulated as a constraint optimization problem. So what you're going to do is you can pick one of these, but here I just wrote down, you want to maximize the short-term revenue with the constraints that your short-term user satisfaction is greater than some constraints that you have set for your product. And your short-term advertiser satisfaction is again, greater or less than some constraints that you've set for your product. So you took your product kind of long-term revenue goals, and then you broke it down into this constraint optimization problem. And now you need to solve this optimization problem. And there are many ways to solve it. I just put down the simplest way, which is can be solved via the Lagrangian relaxation. So you have maximize revenue plus some lambda times user satisfaction and lambda times advertiser satisfaction. Typically, these satisfaction metrics don't have to be only one. So you may have a set of lambdas associated with a set of short-term user metrics, and a set of lambda A is associated with a set of advertiser satisfaction metrics. And these metrics can be correlated too. Now, revenue is typically, you get paid when somebody clicks on it, right? So it's really the probability of somebody clicking on an ad times the price that the cost that the advertiser is willing to pay you for that click. Now, typically that price or the cost is only determined after you run the auction. And this function that I just wrote is your ranking function. So because it's based on the output of your ranking function, we don't typically use revenue. We use something called welfare. And welfare is the advertiser comes in and says, hey, I'm willing to pay up to this much for a click. And so we use welfare, probability of click times bid. Now, if you have a single slot, you have a single advertiser, these two could be the same. Or if you have a CPM auction, which is called I pay for an impression auction, these could be the same, but we typically use welfare here. So it's maximize the welfare given these user satisfaction and advertiser satisfaction metrics are going to be satisfied. Okay, so now you have boiled it down to a single math equation. And so you got to now compute these probabilities. You've got to figure out your metrics first, and then you got to compute the probabilities and the metrics at runtime.
Rukmini, we have a question that just came in. Can you elaborate a little more on the difference between revenue and welfare?
Right. So what happens in typical search engines is you get a query, you take a set of documents, you look at the relevance of those documents, and you rank the documents by relevance. In advertising, you don't really rank the documents you don't rank the ads based off of relevance. You rank based off of an auction. You run an auction to say who's willing to pay the most for that first spot, who's willing to pay the most for that second spot. So you're ranking based off of not just are you relevant, but you're ranking them based on are you relevant and the willingness to pay or the valuation for that slot. So what happens with revenue is the willingness to pay. And it usually, we run what is called a generalized second price auction. So the ad that takes the first spot pays the minimum necessary. So they may be willing to pay $10, but they only pay the minimum necessary to keep their slot. So they may only pay $1 at the end of it. So that price that they pay in the end is the outcome of a ranking and allocation in an auction. And so revenue is dependent on the ranking function, and this is your ranking function. So you don't know the price as yet because you haven't ranked and you haven't priced them as yet. So rather than use the price, what we switch to is the maximum that the advertiser is willing to pay for that slot. So that's the difference between revenue and welfare. Hopefully that's clear. If not, ask me again the same question. Okay, so the most important factor here are your metrics. So revenue or welfare is fairly clear, but what are your user satisfaction and your advertiser satisfaction metrics? And most people think that these are the easiest things to pick. In fact, your metrics, if you ever start your own company and you're designing your own product, you should put the most intelligent people on your metrics. The statisticians and the metric design folks, the people who ask the hard questions, why click-through rate or just clicks are not good enough, those are the right people to design your metrics. Don't let your salespeople design your metrics. So how not to pick your metrics? I'm just going to give you an example. So the query here is how to pick a mattress. And on the left-hand side is your control, where we're showing up to four ads here, and you can figure out the ad using the ad slot here. Okay. And on the right-hand side is your treatment. And all the treatment did was increase the white space between the two ads. Now, what happens when you increase the white space between the two ads is you actually pushed this organic content, which says, which is an answer, it's like the perfect answer saying science-backed tips to pick the perfect mattress. You pushed it below the fold. Now, what this does is it actually increases the clicks on your ads because the user is no longer seeing that perfect result. So they may actually click and interact with your ads more. But is that the right thing to do for the user? Or would you consider that the left-hand page, even though it has fewer clicks than the right-hand page, is the better result for the user? So it's easy, like when you have metrics, it's very easy to game your metrics. In fact, changing the font, changing the color, if clicks are the metrics that you go with, oftentimes it's very easy to fool those metrics. This is why we typically recommend picking a couple of metrics, even if they're correlated metrics. And in fact, we evolve these metrics every year. So when I started with, I had, I think, 2 user metrics. Now I have about 6 of them. Not all of them are constraints, but many of them are like watch metrics. And in fact, we even diagnose or run diagnostic flights to game our own metrics to understand how it can be gamed. And as a product owner, if you remember, your long-term goal is to grow long-term sustainable revenue, and that's a factor of long-term user engagement. If you don't pick at your metrics and throw darts at them, it's very easy to build a product that actually won't grow long-term sustainable revenue. So I just wanted to give you some sense of the fact that when you build your product, in fact, spend an entire day just kind of picking through your metrics and see how to break them. And if it's very breakable, then you know that you don't have the right set of metrics. Okay, so how do we do metrics in the trenches? And I've just given you a few ideas here. So what we do is we don't use only clicks because, as I said, clicks are gameable. So we use user agnostic relevance metrics. So we label our ads and have judges tell us, hey, this was how to pick a mattress was the user's query. Is sleep mattress the right ad to show to this user for that query? We use implicit user feedback. We use click-through rate as one of the metrics, but we also check if these clicks are long dwell time clicks. So the user clicked on an ad, went to a page. Did they spend sufficient time on the page, or did they come back immediately? Now, even that is gameable. If you make sure that your landing page is kind of slow, like slow to load, we can actually calculate a long dwell time for you, but it's actually just not loaded as yet. So even that metric is actually gameable. The other thing we do is we look at the ad load on the page. So for instance, that white space example, we look at the number of pixels taken by ads, because really the user is coming to interact with your app for the content on the app, and the ads are just a mechanism by which we make money. So we want to make sure that we don't show too many ads on the page. And we use a combination of all of these metrics. For advertisers, again, click-through rate is a great metric for them because they want leads to their page, but we look at long dwell time clicks for them. And then if there is a purchase or there's an activity that happens on the page that the advertiser really values, they indicate that back to us and say, hey, if someone signs up for my signs up for my newsletter, that's a conversion for me. Or if somebody follows me as a chef, that's a conversion for me. So those two are their most critical metrics. But then there's also the quality of the match. So typically advertisers in a search engine, they bid on queries. They say, hey, show me up for the best mattress. Sleep Mattress will bid on best mattress. Now I can show them for some convoluted mattress query. The quality of the match may not be that great, and they care about that too. They want to really be shown on queries that are close to what they really care about. So we have picked these metrics now. And so if you remember, we have our optimization problem, we have revenue, we have user satisfaction, and we have advertiser satisfaction. Now you're going to engineer the solution of your product. So I'm going to use a search engine, but you can use your own product in your head and walk through the same scenario. So that's the optimization problem you're solving. The user came to your website and typed in your search engine, they typed in Surface Pro X. So they're looking for a Surface laptop, and you want to return a set of ads for them. Here I showed two types of ads. The top ads are called product ads with images and prices. And the bottom ad is a brand ad from Microsoft itself for a Surface Pro X. Okay, when the user query comes in, you actually don't know any of these components. So you've got to predict or estimate all of these components. So what's the regular flow that you would have? And it's typically a very standard flow. So the query came in, you need to match ads to this query, documents to the query. Typically in 5 or 6 years ago, the advertiser would have to tell us everything. This is the description, this is the headline. Right now, we generate many of these things. In fact, we can auto-generate the ads entirely if you give us your URL. So we generate the ads. So we use NLG techniques for that. And then, because you need to solve this optimization problem, we start predicting the metrics. So if you remember, I said user agnostic relevance is a metric. So we predict the probability of relevance given the ad and the query. We start predicting the response metrics. You need CTR, so you predict the probability of click given query ad user. You want dwell time, so you predict the probability. What's the likelihood that it will be a good click, long dwell time click given the click. And you wanted to, for advertiser satisfaction, you wanted to look at conversions, so you predict the probability of conversion given click. So you're beginning to predict all the metrics, all the components of the metrics that you need for your optimization problem. At the end of this, you generate the ad bids, you run your optimization, you run your auction, you lay out the whole page. Do you show product ads up here or down? How do you lay out the page? You lay the whole page out and you show the user the whole page. And so this is a very typical workflow. And every block of this workflow is essentially an AI engine in itself. And if you think about matching has become, between matching and generation, these are NLR, natural language representation and natural language generation problems. These are all very large scale classification and regression problems. The ad bids or the auto bidding and the optimization are, you can treat them as contextual bandit problems, but typically they're all reinforcement learning problems. You're trying to maximize long-term revenue. And then you want to play around with the layout of the page, and that's typically through a contextual bandit type of scenario. So if you think about it, every box here is an AI box that you have to build out. And because we won't have time, I'm just going to use two boxes to describe the complexities. The first one is a simple retrieval. How do you retrieve the ads given a query? And the second is a user response prediction, because this is where causality plays a big role. But all of these boxes have, really, really interesting problems. And in fact, if you can think of any of the large scale deep learning models like GPT-3 or BERT is now old, but any version of BERT, all of those are used in one form or the other in this type of a production system. So we'll start with the matching, just retrieving the ads to the query. And most of you are aware of typical BM25 or information retrieval, the standard old school methods of matching an ad to matching two pieces of text. And in 2016, we moved from all the syntactic and the semantic type of matching techniques that we had. We moved to deep learning, and we built the very first deep learning matching service at Microsoft, which was called Axon. And the idea was you would embed the query in a certain space. You could embed the ad in many different spaces, and you would have a neighborhood graph search algorithm that would run online to pick a set of ads. If you remember the picking of the ads, you can actually have higher recall because you still have to go through all of these pieces, and the ads will get culled as you go through these prediction problems. So so this was a really large scale deep learning vector search system, and it immediately showed us a lot of gains in revenue. And in fact, the matching was a little bit more accurate too. And we actually then released it. It became an org-wide deep learning vector service, and then it was later open source. So this was just to kind of indicate that we see something in the industry, or MSR talks about something, and then very easily these technologies come back into the production ecosystem, and you start using these things in the production ecosystem. It's not simple to bring something from research into production. So I do want to talk about that. This was in 2016. In 2020, we are now in large scale natural language generation, natural language representation. So here I talk about a natural language generation task where we want to rewrite this query, image royalty free, to free copyright images. And to do that, we start with transformer as an encoder ecosystem. We have word embeddings and position embeddings. We have our training set, which is typically query and keyword paired training data sets that we provide as inputs. Once we fine tune, we can then have a decoder at runtime, and the decoder is a constrained decoder because in the end, we really want to match the query. We want to rewrite the query into keywords that the advertisers are bidding on. So we have a constrained try decoder. And this ecosystem, again, I think it's live now and again going through a lot of changes, but immediately it gave us better revenue. The matches were significantly better, especially as we moved to very large scale transformers. And again, this is just to tell you that if you think of the technology that's being built in the academic community, a lot of that technology is actually being leveraged in many of these production ecosystems. Now, what are the challenges with deep learning in production? Now, these models are getting bigger and bigger. I don't know what GPT-3 is at. I forgot, but these are like very, very large scale models and they are not servable. We cannot serve them in production. So one of the areas that really took off inside my team was, can you use these models as teachers and then distill the knowledge into student frameworks? And in fact, I'll present one of them, but that has already become passé and people are moving on to other types of student frameworks. So serving costs are very, it's very challenging. Like if you really need to have a high throughput, fast latency system. And so having these very large models at serving time, unless you can come up with ways to reuse the same inference multiple times, it's hard to do that in production. The second one is offline inference cost is also very expensive. So you need dedicated sort of GPUs often, and we are typically working on billions of documents, and these documents are constantly getting updated. So it's not like you do a billion documents and then you're only doing delta set of documents. There's a lot of churn in this document database. And so your inference costs are also very high. And so we have a dedicated team that just works on optimizing, speeding up inference. And in fact, that's also used all across Microsoft. I'm not going to talk about the inference work here. It's part of, we open source a lot of that work also. So you may find people on my team, their names when you start using some of these speed ups for inference speed up. And finally, most of our products are built for Windows, and Windows is global. So in research world, you can really stick, or in Kaggle, you can stick with a specific problem and you can solve for that specific problem. And often the language is like a single language, or it's a single market, or it's even a single category of products. But when you're building something at our scale, you cannot just say, I will only have this model for English speakers and English queries. We really need to support hundreds of languages. In fact, even in the US, we got Spanish advertisers complaining to us, hey, you are really not supporting Spanish as well in the US as you should be. So if you think about the technologies that you're building, ground up, just out of the gate, you should be thinking global. Don't think of just saying, I'm going to build this for a specific language. And luckily for us, the technology can handle hundreds of languages with all the multilingual transformers and multilingual models that exist out there. So the student framework that we first developed was called the Twin Tower framework. And the Twin Tower framework, what it did was, it said that the query is dynamic. It's coming at real time from your users. But the documents are actually, just like in information retrieval, BM25, you would index your documents. Your documents are actually already there. So you could just run offline inference and create the embeddings for them and just upload the embeddings to your serving system. And so rather than building a joint set of embedding layers, you have a query embedding set and a keyword embedding set, and they have a crossing layer. And these are trained together using all your training data. Now, your keyword embedding can actually be many layers and can actually be deep. Your query is typically smaller, but remember, your query only has to run once. Your documents, you can have thousands of documents, but your query is only once in a single call. And so this ecosystem actually worked out of the box beautifully. And when we launched it, it actually improved the query keyword defect rate. The first application that we had was the query keyword defect rate. But then we took this student framework and we used it across problems. So this framework is actually, the student framework is used across multiple, like audience targeting in news feeds, which is not even an ads problem, click prediction. We use the same framework across multiple different problem statements. Now, a combination of this student structure as well as other student structures that we have developed and multitask learning is becoming highly popular across many of our products, many of our problem statements. And so what the interesting thing I'm seeing happening is that they are not as accurate as your teacher models by design because they don't have as many parameters, but they're getting very close. Like you are losing a couple of points of AUC, which, that sacrifice is well worth it, given that these actually run during production and you can constantly keep them updated now that you also have an optimized inference layer. Similarly, for cross-lingual models, initially when we started only English, we were only building these really large models for English. And thanks to Microsoft Research as well as the open community, we have very powerful multilingual teachers. And the last one, Turing, is Microsoft's own very large scale natural language representation models. And these are universal language representation models. And I show you below here, we built a commerce universal language representation and compared that to XLMR, which is at that point in time was the state of the art. And we saw some nice gains using, so the primary difference between the two was that we also leveraged all our training data when we built the base representations. Again, I think we have been using very effective student models, and these student models are evolving. What is interesting is the teachers, as they get more powerful, we are able to leverage these teachers out of the box. As long as you have students that are able to distill the knowledge, you are able to actually take these teachers and put them online. And so there's work going on both with the powerful teachers as well as the effective students. So that's on deep learning. And so we're going to switch tracks and switch to predicting the user response prediction models. And here, I think most folks think this is the easiest problem in the world. People click on ads, you have labeled data, you just have to build some kind of a fast rank model or decision tree model or random forest model. How hard can this problem be? And in fact, this is the one area where bias plays such a big role in our in the modeling, that from the very beginning, even before causal ML was popular, we have always had to work towards debiasing the problem. And I'll come to that in a slide or so. So we have some of our largest models are the probability of click models, because if you imagine your optimization problem needs revenue, and if you can't predict the probability of click, your revenue estimate is going to be incorrect. And so this model, for instance, has 20 billion parameters. It works off of about 3 years of data now, and it's updated every day. And it's primarily, this is one of the components of the full model that we use. And this model actually is primarily so that we can improve the modeling on the tail. And by tail, I'm being very generic. So you can have tail queries, so queries you have never seen before. You can have tail ads, like ads you have never seen, or advertisers you've never seen before. And you can have tail users you have never seen before. So this model actually has query embeddings, user embeddings, and ad embeddings. And one unique, and we use dropout to estimate the confidence score. So it also produces not just a probability of click, but a variance estimate so that you can use it for exploration. Now you'll observe that I've set aside the position features, and it's not part of the embeddings. And that's because there's a lot of bias in the position features. So if you think about the causal graph for a click, and I have a simplified causal graph here. The simplified causal graph tells you that the click depends on the position. So if you show the ad at position 1 or position 2, the probability of click will vary. The ad at position 1 will get more clicks. The click also depends on the ad quality. So if the ad is more relevant, or for that Surface Pro X, I showed a Microsoft ad for Surface Pro X, it might attract more clicks than if I showed a Mac ad, because people are really looking for a Surface ad. And so you have this causal graph, and the observational data that you're collecting comes out of this causal graph. So you have ranked by some mechanism, and then you show this ad on position 1, and you decide to show this ad on position 2. If you just take the clicks from that data, then the ad in position 1 is going to get more clicks, but you place that ad there. So if you really want to collect unbiased data, you have to break the causal graph. So you have to break the causal connection between quality and position. So how do you do that? The alternative is we had debiasing methods like intuitive ways of debiasing the observations. And that's what we were using until we came to causal ML. So what we did here was we broke that we intervened to break that connection between quality and position. So you randomize, take a set of ads and you randomize across positions and you collect your position information. Now, this intervention is pretty expensive because even though you break that connection, it has a first order cost. So you're not showing the Microsoft ad on the first spot. You're going to show the Mac OS ad on the first spot. And the user is not going to be as happy as they were with the Microsoft ad. So it has a first order cost because you have unhappy users and you will lose money. And so we collect very little randomization data. And you really need to use this data to the best of your abilities because that data is pure gold. It is the most unbiased, from a position perspective, the most unbiased data that you have. So what we do here is we use, and I'm just giving you a simple idea here, where we use causal transfer random forests. And the idea on the left-hand side is a typical system you would build. You will have an observation data set, you will build your trees out of it, and you will estimate the probabilities of your click versus no click probabilities at the leaf nodes using that observational data. Instead, what we did was we did the feature selection or the tree construction using the randomized data, because that will really focus on your the causal features that cause a click. And then at the leaf nodes, we use the observational data to predict the probability of click. And this actually really works beautifully. We also use this in production, but we also use this in our counterfactual platform that I'll talk about at the very end. And this works beautifully. Now you have very little data. So, and I showed you with the causal a random forest, but if you were to use very large scale DNNs, how would you use this data? The same ideas can be used, but you have to be smarter about how you group things together to use the data. So this is our full advertising ecosystem. Every box has sets of models. We have more than about 200 machine learning models. We run about 2,000 odd online experiments, and a set of these experiments are successful. Many of them just are null hypotheses, so they don't go out, but some of them are successful and they actually get launched into production. But this ecosystem is very rich in terms of the types of modeling that you can do, the types of experiments you can do, and all of that rests on the bed of the set of metrics that you have. It's very easy to super optimize or overfit this ecosystem if you don't have the right set of metrics. I'm going to move on to the next. So you have designed your system, you've built your system out, and now your system is running in production and it's making money. And every day somebody complains to you, hey, why does it make less money this week compared to last week? Or it made more money on Sunday, what happened? And you have to say, oh, this Sunday was Mother's Day. And over time, you realize you get this question every day because it's a volatile marketplace. So now that you have this production ecosystem, how do you keep it running smoothly? And I talk about three things here. The first one is experimentation. You have 200 ML models. They get stale very fast if they're not being trained. They're not learning online, or you don't have a way to update them. And so for us, we have, most people think of A/B experiments, they think of a single number line, a single line where you run, I run experiments, Karen runs experiments, all of us run experiments, and we get a certain amount of traffic to run experiments. That is too restrictive. So what we do is actually we have parallel number lines. Say I'm the relevance person, I get my own number line, and Karen is running the probability of clicks, so she gets her own number line. And then these are interacting, right? So now her experiment is interacting with my experiment. So there's some subpopulation in my experiment that's seeing both these experiments at the same time. We just believe that her experiment is going to be equally divided between control and treatment, and so you can take care of this. But oftentimes that's not the case. So we have many parallel number lines. It's a highly configurable flighting system. When you set your experiment live, there are checks that happen. and there's continuous monitoring to make sure that, some of the metrics are not degrading or revenue is not degrading. And then we have an analytics team that builds tools to see, okay, Karen's experiment and my experiment actually interacting. And if that interaction happens, we cannot release both at the same time. So say both our experiments are successful, we have to pick one of them to release and then wait for the other one before we release it. In fact, experimentation is not just on users. We also provide experimentation as a service to advertisers. So they can test, if they have a theory that I should raise the bids for these type of keywords, they can run an experiment and see if they see the return on investment for that increase in bids. So that's experimentation. Your model metrics have to be continuously monitored, and your model has to be evaluated on the randomization data. I mean, that's your purest, your gold data set. You can also evaluate it on your on exploration data, but if you're evaluating your model on its own output, typically it will look pretty decent. It's only when you start comparing it on more data out of its scope that you actually see the problems with your model. We also evaluate models on different slices of data. So for instance, say your model aggregate AUC improved, but you for advertisers that are new or users that you're new, a cold start problem, your model is much worse. Or for instance, say you have a set of missing features, like there's always this case that offline when you run your training assuming 100% feature coverage, but when you go online, maybe there's 5% missing coverage, and on that set your model is terrible. So we slice and dice it on different slices, and you have to monitor your features. It's very easy. Say you're using features from some other team, like I'm using location from some top level team, and suddenly their location model changed, and suddenly my users are being identified in a different way, and my model hasn't seen that identification. Its metrics can change, so you have to monitor your features in production. And finally, advanced analytics. You have to completely, continuously evolve your metrics, and you will constantly get this question as to what happened today. In fact, we have an entire team that only monitors. It's called a live marketplace team that's monitoring the marketplace continuously. And they get this question every day as to what happened today. What do you expect to happen tomorrow? So explainability and counterfactuals become your close friends. If you can explain what's going on, and it's hard to explain what's going on. In fact, every time Trump would tweet, we would see something change in our ecosystem, and it's hard to explain that. But, as long as you're trying to build tools towards explainability and you have ways to counterfactual predict what's going to happen in the future, you're in a much better place. And this is a hard battle to fight. Most people say, why don't you just focus on new features in your product? So when I put people on advanced analytics, and the reason is because you want a stable ecosystem. You want a stable ecosystem for your product. I don't know how much time I have. I think I have enough time to go through one of the explainability components. So if you remember, this was the first slide that we started with for designing an advertising product. And I described how your revenue is a function of the user, system, and advertising. So if the user base changes, say, for instance, when coronavirus happened, the users, stopped buying expensive products, but we saw a lot of grocery sales online. So we went from expensive products to cheaper products. So this is a function of the user, the supply, the mix that you're getting. The advertisers could change. So in March, a lot of the big advertisers, just like the travel advertisers, for instance, completely stopped spending because there was nobody traveling. And so you see a big dip in your ecosystem, and that's because an entire slice of your market went dark. So that's a function of the advertiser. And then your system, because you have so many models and daily deployments, and you're shipping experiments and shipping, features all the time, you easily can introduce a bug. And so your system can also cause instability in your ecosystem. So say you want to explain one of these dimensions. So for instance, what will typically happen is there's a forecast. That brown line is your forecast, and the blue line is what you're observing. Say it's clicks. The brown line is the forecast for your clicks, and the blue line is what you're seeing in your marketplace. And suddenly on April 17th, the clicks really jumped high. Actually, the week before itself, it went high. And then somebody comes to you and says, hey, what happened here? So I'm only going to take supply. So three things could have happened. Did your supply change? Your users suddenly started shopping and clicking on ads. Your advertisers changed, new advertisers, Amazon just came in with a whole bunch of demand. Your system changed and you're logging clicks incorrectly, for instance. And so you want to know what caused this to happen. And I tried drawing a causal graph here, but it's just got too many. The stock market, for instance, when the stock market does well, suddenly people click on ads more. We don't really understand the causality of this. Could be just a correlation, but it's a unstable ecosystem. So how do we, if you want to just explain supply, how do we do this? So what we do right now is the bottom you're seeing, say the month of March, I observed a set of queries, users, query categories. These are all my supply side features. And I observed a certain revenue in the marketplace. I predict the revenue. I build a model that predicts my March revenue given my March supply. And that's my model of prediction. Then I take my March model and I run it on the April supply. That's my analysis period. And I observe what the model tells me on the April supply. If the model says that your supply, your April supply has actually gotten way better, just in terms of supply, people are clicking more, they're issuing more commercial queries, then your predicted KPI will say that, hey, a lot of your actual revenue gains are not coming from anything that the system did or anything that the advertisers did. It's just that your supply got better. So it's like creating a synthetic control for the month of April. And what we do is every month we recreate the synthetic control because the system is changing. So for the month of May, I now have a model that can tell me how the month of May could look. And so when I go through May and I hit May 9th, and on May 10th, somebody asked me the question, I go to the dashboard and say, what did my April model say for March 9th? And it shows that the revenue was expected to increase purely based on the supply characteristics. So you can now do the same for your demand characteristics. And if you have supply and demand, then you can isolate your system. It turns out demand is a lot harder to do than supply, but you are slowly building explainable pieces that you can then componentize and break it down and say, okay, it's not my supply that caused this change. It must be the demand and system. Then you look at your demand, you explain your demand away. And if neither of them can explain it, then something in your system changed. Okay, so where do we go next? And I just wanted to, the reason I brought the last two topics, the click model and the explainability, is that when we design our modeling ecosystems, we're always building hindsight-based model. We're looking at the data that we've collected so far, and then we build our model based off of that data. The reality is we don't live in a static world. And so the probabilities and the density functions are constantly changing. It could be changing because there's some intervention happening, like this virus that happened, or it could be changing because the system is changing. People are putting new features out, or users are interacting with your app in a different way. And so if you haven't read this book, and many of you in this, I'm pretty sure have read even the textbook, his causality textbook, but this is an easier book to consume. He has these three graphs, and where Juriapal claims that most machine learning systems are sitting at the bottom of the rung with association. I would disagree. I think we are in the middle. We are in intervention right now, causal ML, and it's a C, so you can easily get drowned. So you need to be very careful what type of problems you pick for causal ML. But I staunchly believe we are in the middle in interventions, where we are actually trying things out and seeing how the behavior looks like, and seeing if we can model the reaction to the intervention that we tried. And we actually have a counterfactual platform where we can predict if the advertisers' bids were to change, or we took out these three advertisers from the ecosystem, what would the counterfactual look like? We have a counterfactual platform that can predict the first order metrics. Now, counterfactual modeling is a very different problem, because in that case, you don't have any observed data, right? You're going to actually re-rank the ads based on, say you removed Amazon from your ecosystem. You're going to re-rank the ads based on Amazon no longer being there, and then predict how the user is going to interact with those new set of ads that you showed them in a new ranking that you showed them. And so you need to build counterfactual models to do that. And so there's a lot of interesting work happening in the counterfactual space as well as in the second order. How do you predict second order metrics, not just the first order metrics? So I'm going to stop with that, and I hope that this was a useful run through a production ecosystem, and I'm happy to take questions or comments from any of you.
Great. And please add your comments in the chat, or you can unmute and ask a question. I had one, if you could address just when you're thinking about biases, and there's a lot in the news in the last few years on ad platforms, maybe serving up to a certain ethnic group, some ads inappropriately or more heavily. Where in this system are you putting in controls to address those kind of potential biases?
So there are two places where, this is not a full solution. So one place is where the privacy controls happen. So Microsoft is very strict about the privacy controls. And so, for instance, California has a law of 14 and under, we don't target. In those cases, we just don't take any user features at all. So they're just all blanked out. Now, we do the same for sensitive demographic features like gender, race. We don't use these features, but we know that a combination of other features can predict these features. And so that's not a full solution. So we actually try to identify bias by playing around with this, if the counterfactual of what if this person had a different set of characteristics, a different location, different IP address. I don't think we have a really simple way of dealing with the problems. And these are highly personalized ecosystems. And so I wouldn't say we have solved for all of those problems, but we are making attempts. So we kind of blank out certain sensitive features entirely from the entire ecosystem. Yeah.
Great.
There was a question online.
Yes, a few. Let's see. The ads workflow is constrained by response time and needing to publish results as quickly as possible. So how do you balance the trade-off of algorithmic accuracy and effectiveness with speed? Do you invest in new algorithms, faster hardware, other directions, all of the above?
I mean, actually, we do a combination of all of them. So what we tell our scientists and engineers is build the best model that you can. And typically, they build the best model, and then I go to my systems team and say that, I can obviously prune the parameters of this model to fit in your system, but can you build me the best system that can fit the entire model, or at least give me the same accuracy? And so it's a combination of things. We started with, in fact, simple things like separating out your data and compute, parallelization, anything that can be parallelized, we parallelize. Better hardware. In fact, we even use FPGAs. So we code to the hardware in our compute, especially for the deep learning models. And so all and many of these combinations get tried. The one thing that we won't compromise on is agility of experimentation, because that's where a lot of the gains come from. And so FPGA, for instance, we know that the current system that we have to code the model into the into the hardware for the system, which means if you want to experiment with a lot of models, we typically experiment with CPUs. And then once we pick the best model, then we can put it in FPGA, but then we have to test that it's working exactly as we tested it in the experiments. And so there is some loss of agility, and we try to even bridge that gap for the loss of agility.
Great. Here's another question. Can you say a little more about how you are modeling the counterfactuals? For instance, modeling counterfactual user actions when exposed to a different set of ads.
So if you remember, I collect the randomization and exploration data, and that actually gives me a wider space of ranking and user actions than I would have observed with my mainstream, my observational system. And so we use the randomization data. In fact, the causal ML, the random forest that I showed you, was for the counterfactual click model. So any counterfactual system, the hard part is not retrieving the documents, and we basically log everything. So we log everything that we filtered, so you can replay the entire auction and you can change things about the documents at runtime. The counterfactual problem you're really trying to solve is how will the user react to this new set of ads. So the counterfactual click model is the biggest piece of the puzzle. And for building that click model, the one advantage you have is you can construct that click model in the context of the entire page. You're not doing it runtime, right? You're laying out the ads. It's in the context of this big page or your app. You actually know the session of the users. You even know the future of what the user had typed, although that is impacted by the ads you show. So you can use a lot more information of what the user is seeing and not just the ads, but you're constrained that it's a new set of ads. And so you have to predict the probability of click. And that's a counterfactual probability of click. And that's actually the debiasing becomes even more important in that ecosystem.
Mm-hmm. We just have one more question here, and I know we're at the hour, and a lot of thank yous for the talk, by the way, coming in. But how do you decide how much randomized data to collect, since it affects both the users and the bottom line, and presumably requires a lot of approvals and buy-in from other parts of the organization?
Right.
How do you manage the trade-offs there?
So we used to have a small flight that would run randomization, and we quickly realized that's not the way to maintain randomization. It's well controlled. You can see exactly the amount of money you're losing, but then you have to maintain that system. It falls to disuse, parameters change, the latest model is not on it. So what we do is we do both exploration and randomization in production systems. So the exploration is built across all the models, any model that goes online, especially if you're making a filtration decision, a decision based off of that model's output. We do exploration, and some fraction of user queries are always randomized in production. This means if you run an experiment with a new model, your new model is still collecting some randomized data. These are very few samples, so we pool them all together. But for instance, say you change the UX and you introduce a fourth ad and you only used to have 3 ads. Because your randomization is in production, you're now collecting data about that fourth ad. And so the right way to design the system is to have randomization from day one. So nobody questions you as to, hey, why did you lose so much money? You can't lose money that you didn't make in the first place. So this is how we get by. But there's a lot of education that we do of our executives, of our sales, to explain to them that that data is critical for you to give an unbiased auction to the advertisers. So they understand it also that, for the sales team, for instance, if you want to treat your advertisers fairly, you do need to collect this data.
I did get one final question. If you could just touch on the difference between exploration and randomization, both being put into production.
Yeah. So exploration is where you have your model and your model has a variance or confidence score associated with it. So for instance, the probability of click will say, this is my mean estimate and here's my variance. And then rather than use the mean estimate, you flip a coin and you do, within some plus or minus sigma of the mean estimate. What that does is, if you, for instance, say your filtration was on a threshold of 0.2, because you are now exploring around 0.2, you will let in some samples with 0.18. And if you were making the incorrect decision, when you label the data, your labels will say, hey, you filtered this ad out, but actually this ad was not a bad ad. So you're collecting data around the filtration decision points. That's exploration. Randomization is saying there's no model. I'm just going to completely bypass the model's decision-making power and just take a set of ads and randomly allocate them to these positions. That data is pure gold for positional bias, because that data is just purely looking at, independent of the quality of the ad, I showed this ad on position 1 or position 3, what clicks did I get? Randomization is way more expensive than smart exploration. So that's why we collect a lot more exploration data and some randomization data.
Well, this is fantastic. And sorry we have to end here because I'm sure we could go on for another hour. But thank you so much, Rukmini, for coming.
Yes.
and really appreciate the talk today. It was great.
And
Okay, that's good.
Yes, and I'm hiring. Actually, my entire organization is hiring. But look me up. If you are looking for, I guess internships. Most of you already have internships. But if you're looking for, you're graduating, you're still looking for a full-time role, we are hiring. So reach out to me, and I'll get you connected inside. And thank you, Karen, for inviting me. I always enjoy giving these talks and hearing the questions. And these were, you guys really followed the talk, because the questions kind of sounded like you got what the talk was about.
It was excellent. Okay, thanks again.
Thank you all.
Thank you.
Bye.
Good evening.
Bye.
Bye.